Good afternoon and welcome to week 10. Week 10 we're going to cover thunderstorms and tornadoes. And just want to let you know that this material that I cover in this video, it is in chapter 10 of both the 7th and 8th edition of the books, the textbooks. So let's talk a little bit about thunderstorms and tornadoes today. All right, so let's take a look at some of the characteristics of thunderstorms first of all. Now, a thunderstorm is technically a storm containing thunder and lightning. Okay, convective storms that form, they are typically convective storms. Convection meaning the air is rising. As the ground is heated, the air wants to rise. It's less buoyant. It's more buoyant. It wants to go higher up in the atmosphere. So convective storms, they form in rising air. So you got rising air motion, usually by a heated surface. That's what typically causes thunderstorms. There are several triggers. All right. One of the examples is random turbulent eddies. And when I talk about eddies, I want you to think about just small little pockets of air that are kind of swirling around. Unequal surface heating. That's an example of a sea breeze, for example, when you get those pop-up thunderstorms. Along the Gulf Coast, for example, or in the Florida Peninsula in the summertime. That's due to unequal surface heating between the land and the nearby water. So you get the air to come in from the water to replace the rising air from the land that's over the land, and you get these thunderstorms that develop. And then there's also terrain, mountainous areas. When you have a valley breeze, or when the slopes are heated much more greatly than the lower valleys, you typically get rising air over those mountain slopes. Now, severe thunderstorms, what is the criteria for severe thunderstorms when we say severe? That would be large hail, wind gusts greater than or equal to 50 knots, or a tornado is present. Okay, so that's the severe thunderstorm classification criteria. Now, there's a couple different types of thunderstorms. There are ordinary cell thunderstorms, and then there's ordinary. When we talk about ordinary cell thunderstorms, I want you to think of air mass thunderstorms that tend to form where the wind speed and wind direction do not abruptly change with increasing height. So ordinary cell thunderstorms, also known as air mass thunderstorms, typically occur during the summertime where you have the land being heated to its greatest potential. And there is really a lack of wind shear. When I talk about wind shear, I'm talking about a change in wind speed or direction with height above the ground. So with ordinary cell or air mass thunderstorms, you typically do not have that increasing wind shear, that rapidly changing wind speed and direction with height. Now there are 3 stages to an ordinary cell, also known as an air mass thunderstorm. There's 3 stages of development. There is the cumulus stage, the mature stage, and then finally the dissipating stage. And they do occur in that order: cumulus, mature, and dissipating. In the cumulus stage, you typically have rising updrafts. Updrafts being rising air currents, convective currents. With a mature stage, you have both updrafts and downdrafts. And during the mature stage is when a thunderstorm is typically at its peak intensity. And then finally, with the dissipating stage, you simply have downdraft of air. Colder air is being dragged down from higher aloft towards the ground during dissipating stage. Now, there are other types of thunderstorms beside the ordinary air mass thunderstorms. You have multi-cell thunderstorms, and what happens with multi-cell thunderstorms is you get a larger number of thunderstorm cells. They're each in a different stage of development. So one might be in the cumulus stage. The thunderstorm next to that thunderstorm might be in the mature stage. Another thunderstorm may be 5 to 10 miles away, and the general area may be in the dissipating stage. So the stages of development can vary with multi-cell thunderstorms. And multi-cell thunderstorms form in a region of moderate to strong vertical wind shear. Okay, so with multi-cell thunderstorms, you do have the wind shear, that wind speed and direction change with height. Now, associated with multi-cell thunderstorms is what's known as a gust front, which is typically the leading edge of the cold outflowing air. Have you ever been outside and you see this dark wall of clouds coming towards you, and you know it's going to be thundering. You know there's a thunderstorm approaching. The sky is really dark. What happens is, out ahead of the leading edge of those thunderstorms before they get to you, where you're standing watching it, there is a strong downdraft of air. Much colder air from aloft is being dragged down to the surface out ahead of that thunderstorm itself, and that's known as a gust front. And you'll notice that when you start feeling the much cooler air coming down out of the thunderstorm, you notice how the temperature will drop off. It might be on the order of 5 degrees Fahrenheit in a very short amount of time when you have a thunderstorm approaching in the form of a gust front. Then there's something known as microbursts. Now these are downbursts with winds extending 4 kilometers or less. Micro meaning smaller, all right? There is actually a macro burst, M-A-C-R-O, as well, but in this case we're just showing you the microburst on this slide. And microburst is, again, air that is basically coming downward out of the thunderstorm. It's a downburst with winds extending. When that downburst of air hits the ground, it has to spread out horizontally, and it extends out to 4 kilometers or less distance. All right. Now, there's also what's known as squall line thunderstorms, and this is a line of multi-cell thunderstorms. Squall line thunderstorms typically occur out ahead of an advancing cold front. There is a prefrontal squall line, and what's interesting about the squall lines is the winds do shift and the barometric pressure does change, and it makes it almost seem like it's a cold front passing through, but that actual cold front may be further back, another 100 miles behind where the squall line is. So when you have that line of thunderstorms come in, temperatures will cool off because of the downburst of air coming out of the thunderstorm. The wind may shift, the barometric pressure may rise. That is a sign of a typical indicators of a cold frontal passage in the northern hemisphere, but it's actually just temporary. Once that squall line passes, the winds will shift back typically to the southwest, and the barometric pressure will once again begin falling. And the temperature will start leveling off or maybe even increasing a little bit after the squall line passes. So you just have to be mindful of that. There's something known as a bow echo in association with squall lines, and this is a bow-shaped radar signature. Wherever the bow bulges out the greatest, that is where you have the strongest downdraft of thunderstorm winds. Okay, so you can get some really bad, you can actually get some pretty good damage with squall lines, especially where there's a notch. It's called a notch on a bow echo, and it's on a radar reflectivity image. Now, a derecho is another very intense type of thunderstorm associated with squall lines, and it can produce some really damaging winds. Derechos are long-lasting lines of thunderstorms. Now moving on to the mesoscale convective complex. It is a number of individual multi-cell thunderstorms that grow in size and organize into large circular convective weather system. So we term this MCC for short, mesoscale convective complex. This is a number of individual multi-cell thunderstorms that grow in size and organize into a large circular weather system. You will notice this, especially on enhanced infrared imagery weather satellite. It actually appears to be this huge circular shape, a mass of thunderstorms. And it will also be reflective on your Doppler weather radar as well. Mesoscale convective complexes are really interesting in that they, especially in the Midwestern United States, they can form in the summer during the middle of the night. They do not need the sun's energy to fuel them. So they almost like have all this instability and moisture that just continually feeds off each other. Right. Supercell thunderstorms. When we have supercell thunderstorms, you have very strong vertical wind shear. So there's a rapid change of wind speed and direction with height. A supercell thunderstorm is a long-lasting thunderstorm with a single violently rotating updraft. The other thing interesting about supercell thunderstorms is it has a tilted updraft. So when you have a tilted updraft, it does not choke off, the downdraft does not choke off the updraft with a tilted updraft. Air mass ordinary cell thunderstorms typically have a vertical updraft, a straight up and down updraft. Eventually what happens is all the cold air aloft suffocates or chokes off the updraft, killing the thunderstorm. But with a supercell thunderstorm, there's more of a tilted updraft. And a supercell thunderstorm is long lasting. Okay, supercells are typically found in the central plain states of the United States: Oklahoma, Kansas, Nebraska, Missouri, in that general tornado alley, the central plain states. Now, there's no two supercells that are exactly alike. You have a classic, you have a high precipitation supercell, and a low precipitation supercell, an LP. Okay, so there's three types of supercells: the classic, the high precipitation, and the low precipitation. Mesocyclone is a rotating area, rotating circulation within that supercell thunderstorm. And then a wall cloud is actually the cloud that would be visible to produce a tornado in association with the supercell. So mesocyclones are that mid-level rotation you need. And then the wall cloud is the low-hanging cloud associated with the supercell that is associated with producing tornadoes. All right. With thunderstorms, there's a lot of threats. All right. One of the biggest threats is the flooding. All right. Flash floods rise rapidly with little or no advance warning. They happen so quickly. Many times they're caused by stalled or slow thunderstorms. Large floods can be created by training of storm systems. So when I say the word training with thunderstorms, I want you to think that a thunderstorm continually moves over the same location. So a training of storms, that thunderstorm, thunderstorms keep forming and they keep moving over the same location, producing rapid flooding, sometimes flash flooding, very life-threatening type flooding. And then distribution of thunderstorms. Where do they typically occur? The most frequent region of thunderstorms occurs in the state of Florida. Florida is the thunderstorm capital of the world. It's also the lightning capital of the world. Gulf Coast states in general too, especially during the summer months when you have heated landmass next to the water, the Gulf of Mexico, a lot of sea breeze type thunderstorms develop as a result. Now with thunderstorms, there's typical elements that we normally would expect to see, lightning and thunder being two of those. Now lightning is simply a discharge of electricity, and it occurs in mature cloud storms. Okay, lightning is really created by the electrical difference between the negatively charged particles in the bottom part of the cloud and the positively charged particles in the upper part of the cloud. So ice crystals, where it's really cold in the upper part of the cloud, are typically positively charged. The bottom part of the thunderstorm cloud is a negative charge associated with the raindrops, with the liquid drops. All right, and so when these updrafts and downdrafts move these various charges up and down through the cloud, it results in an electrical difference, or also known as a electrical potential, and this results in opposite charges attract, and you get lightning as a result, and that is the discharge of electricity when that happens. Thunder is the booming sound wave that we're all familiar with. It's an explosive expansion of air due to heat from lightning. So I want you to think about this. Thunder is simply produced by the rapid heating and expansion of an air column within the atmosphere. Things happen so quick. Lightning can be anywhere from 11,000 to 50,000 degrees Fahrenheit. You're heating a channel of air to that kind of intensity, the kind of heat, 11 to 50,000 degrees Fahrenheit. And light travels faster than the speed of sound, so therefore you see the flash first and then you hear the thunder second. Okay, so how far away is a lightning? Speaking of that, you can actually start counting. Once you see lightning and then you hear the thunder, 15 seconds later, the lightning stroke in the thunderstorm is about 3 miles away. All right, so in order to calculate the distance between of the lightning strike, you would observe the lightning, you would count the number of seconds between the lightning and the thunder, and realize this: 1 mile distance is equal to 5 seconds between the lightning and the thunder. If, for example, it took 10 seconds between the time I saw the flash of lightning and heard the thunder, that would be a distance of 2 miles. Okay, So you've probably been around a thunderstorm where you've seen the lightning flash. It was really bright. Maybe it was a cloud to ground lightning strike, and you heard the thunder instantly. That is an example of a very nearby lightning strike. Okay. There is electrification of the cloud. As I mentioned just previously about how lightning is created, you have the grapple, which is like the solid ice, and the hailstones. They fall through the supercooled liquid droplets and ice crystals. These particular hailstones then freeze multiple layers. You have this chunk of ice. It comes down the downdraft, picks up supercooled water at the base of the thunderstorm. Then it goes back up and rides another updraft, picks up another that layer of water that surrounds the ice. When it goes back up, it accumulates and creates another ice layer. And during the process of the freezing, it releases more latent heat. Okay. Anytime that hailstone takes the supercooled water and that supercooled water freezes, adding another layer to the hailstone, it releases latent heat within the thunderstorm cloud. All right, now thunderstorms also have different types of lightning. The lightning stroke is typically a negative charge at the bottom of the cloud. As I mentioned, the negative charges are associated at the bottom of the thunderstorm cloud with the liquid water droplets. The positive charges, there's also a positive charge on the ground directly beneath the thunderstorm cloud. Okay, so you get what's known as cloud to ground lightning when the electrical difference between the charges is too great. You also get what's known as a stepped leader. All right, stepped leader being objects on the ground have a positive charge beneath the thunderstorm cloud. There's a negative charge in the lower part of the thunderstorm cloud. So the actual stepped leader occurs from the ground as the electrical current works its way up towards the base of the thunderstorm from positive to negative charge. It creates a stepped leader effect. Return stroke would be the downward returning stroke. The stepped leader would be the upward directed lightning. Dart leader is another example of something associated with a lightning stroke. Now, types of lightning. There's many numerous types of lightning. There are fork lightning, ribbon lightning, ball lightning, and sheet lightning. There's also heat and dry lightning. Okay, so a fork lightning is exactly that. It resembles where you kind of look in the sky and you see multiple flashes or branches off of one main lightning stroke. That's a fork lightning. A ribbon and ball, especially ball lightning, is a very unique type of lightning in the atmosphere. Sheet lightning is when you just see a flash of lightning. Okay, that's just a flash. Thunderstorms with lightning detection and suppression now. What about lightning detection? How do we know where the latest lightning strikes are? Well, we do have lightning direction finders now that detect radio waves produced by lightning. There's actually networks of magnetic devices that are used to pinpoint locations. And satellites continuously detect all forms of lightning across the whole entire globe, across the whole entire world, over land and water. With thunderstorms, just keep in mind that there's a rapidly, especially with severe thunderstorms and tornadoes, there's a rapidly rotating column of air. Right, and it blows around a small area of intense low pressure with circulation that reaches the ground. So when I'm talking about severe thunderstorms and tornadoes in particular, what is a tornado? It is a rapidly rotating column of air in contact with the ground. It has extremely low pressure within the actual funnel itself. There are different stages of a tornado life cycle. The first stage is the dust swirl stage, the second is the mature stage, and the third is the decaying stage. Sometimes they also refer to that third stage, the decaying stage, as the dissipating stage of a tornado. And typically you have different appearances. For example, in the decaying stage, you would have a more like a rope-like structure. Okay, so here's a great example just showing you a picture of a thunderstorm, what it looks like. In this case, I'm showing you a cumulonimbus cloud. Remember when we learned the clouds? Cumulonimbus cloud being typically associated with a thunderstorm, a very tall vertical cloud that grows to great heights in the atmosphere. Some of these cumulonimbus clouds also have what's known as an anvil shape on the very top as the upper level winds blow the top downstream. This image here shows an example of the developing stages of a thunderstorm. Okay. Now the red arrows in each of these images indicates updrafts or rising convective currents of air. The blue arrows pointing downward toward the ground, coming down out of the cloud toward the ground, those blue arrows represent downdrafts. And on the far left here, when we just see all red upward directed arrows, that indicates the cumulus stage. In the middle picture, I'm showing both updrafts and downdrafts, and that is the mature stage of a thunderstorm. And notice that the mature stage, this is when the thunderstorm is at its most intense. This is when you're getting the heaviest rainfall, possible hail, lightning, a lot of strong gusty winds associated with that gust front, that leading edge of cooler air. And then on the right-hand image is showing the dissipating stage, where you're pretty much dominated. The thunderstorm cloud is now pretty much dissipating because of colder air, just downdrafts of air coming out of the cloud during the dissipating stage. Here's another really nice picture showing you a thunderstorm out over the water. This is looking over the Gulf of Mexico, out over the Gulf of Mexico. Showing you some rays of light from the sun kind of peeking through the thunderstorm cloud. Notice how gray the cloud is and how tall it looks. What we can't see in the top of this image is an anvil shape. This actually had an anvil associated with it. So this image doesn't really do it justice, but there is an anvil shape at the very top. This is a typical, so this is an example of a supercell thunderstorm right here. Okay. Notice the red arrows indicate the rising air or the updrafts. The blue arrows indicate the downdrafts. Okay. Now, I want you to pay attention. See how this is kind of angled? See how the updrafts, the red arrows are kind of angled? They're not straight up and down. They're at an angle. And that's very important because the downdrafts are basically not choking off or killing the updrafts in this case. They're not dissipating the storm. Notice also on the left-hand image here. See the left-hand image? You see those blue arrows like in a horizontal manner. That indicates strong vertical wind shear. You want strong vertical wind shear with supercells because what happens is you get different layers of air, different directions, kind of crossing each other. Eventually what you get is a circulation to develop, a mesocyclone, a mid-latitude rotation to develop in the thunderstorm cloud. And if you get one of these strong red arrows, these updrafts, you get that to lift that horizontal spinning rotation up in the vertical, you get a tornado. Okay. Showing you also in this image, what type of clouds you typically have with a thunderstorm. Like I mentioned, you get this anvil cloud there on the upper right-hand portion of the image. Sometimes you get these like egg or pouch-shaped clouds on the underside of thunderstorms. Those are called mammatus clouds. Whenever you see mammatus clouds, it's a very severe, it's a really strong to severe thunderstorm. Overshooting tops, sometimes updrafts are so strong at the top of the thunderstorm cloud, the updrafts will basically push through the tropopause into the stratosphere, and that's known as overshooting top. That indicates very, very strong updrafts or rising air motion within a thunderstorm cloud. This shows you an example of a microburst. Now remember I mentioned about a microburst being a strong downburst of air. It drags much colder air from aloft, the upper part of the cloud, down to the ground. Once this vertical air current reaches the ground, it tends to spread out horizontally. And remember we said 4 kilometers or less, right? That's a definition of a microburst. Microbursts can be very deadly, especially when it comes to aircraft. There's been a lot of previous aircraft crashes, especially when airplanes are coming in for final approach, for final landing to runways, because they don't see that there might be a thunderstorm in the area around the airport, but they don't know how the winds are changing, and they usually change rapidly. If the airplane were to fly underneath the base of a thunderstorm cloud with a strong downdraft or downburst of air, it could really be a problem. The microbursts have resulted in a lot of crashes upon landing for aircraft because it pushes the aircraft down so fast it just basically pushes it right into the ground. This is an example of the downdraft and the cooler air that spreads out at the ground away from the thunderstorm. Notice on the leading edge of the cooler air there, that bluer area, that circular area under the thunderstorm cloud, that's known as a gust front. Okay. When you start feeling that really cool air, temperatures start cooling off on a hot, humid day as the thunderstorm approaches. Now this is an example of a very interesting cloud. This is known as a shelf cloud. Let's go back to the image. Let's go back one more here. Let's go back one more. Now, I want you to pay attention to the bottom right-hand image of this thunderstorm cloud. Notice that shelf cloud. It's on the bottom right-hand portion of the diagram, and the gust front is basically directly beneath that shelf cloud. So, once you see the shelf cloud coming, this cloud here, once you see this thing coming, you know that you're about to get hit with some pretty strong gusty winds as that gust front is approaching. This is basically the boundary or the border of the gust front. Behind this, you'll start getting the heavier rain, you'll start getting the much cooler temperatures, very gusty winds being dropped down from aloft out of the storm cloud. So this is a very interesting cloud when we talk about a shelf cloud. And now look at this cloud. This is really cool too. Another really cool image of an approaching thunderstorm. This is an example of a roll cloud. You notice the shape is really elongated, it's fairly narrow. It generally indicates a very severe thunderstorm. So again, there's some really interesting clouds you can see in association with thunderstorms. There's also lower scud clouds. A lot of people make the mistake and think the scud clouds are actual funnel clouds or tornadoes. A scud cloud is really just a low-hanging cloud, but it's not associated with any tornadoes. All right, and on Doppler weather radar, now this gets really cool. You can see some really cool stuff happening with thunderstorms on Doppler weather radar. In this case, we have a line of severe thunderstorms over Oklahoma. You notice the area there, the white arrow and the outflow boundary term there. You can actually see, by looking at the velocity product, you can actually see, and reflectivity as well in the Doppler, you can see actual movement away of the outflow boundary. As the air comes crashing out of the thunderstorm, you can actually see the little narrow reflectivity that this is pointing at in this image. That little narrow area of reflectivity known as outflow boundary. So that's basically your gust front. Anything on the other side of the outflow boundary is going to be much cooler air. Here's what I was talking about. I was kind of getting ahead of myself when I talked about the danger to aviation, when you talk about microbursts. As air comes rushing and gushing out of the base of a thunderstorm cloud, this plane has no chance because there's rapidly changing wind currents going on here that this airplane is trying to fly through. And if the microburst is strong enough, it's going to really accelerate right out of the base of the thunderstorm cloud, and it's going to push this aircraft into the ground and most likely result in a crash. Now the cool thing is after a couple of really tragic aviation accidents back in the 1980s, the Federal Aviation Administration, the FAA, decided to install low-level wind shear alert systems. Okay, so there's actually ways to detect the rapidly changing air currents in association with thunderstorms around airports now, which will help give the pilot a good indication of whether he should attempt landing or not. If the low-level wind shear alerts are significant, then there's a good chance the aircraft will divert or go to another airport to land, depending on the aircraft's fuel state, how much fuel is remaining. But this is thankfully we've got more modern technology in place to give the pilots an alert on what's going on as far as the changing low-level wind shear, especially around runways when the aircraft come down to land. Okay, next image here is showing you a reflectivity image of a squall line. Now notice with the squall line how everything is just one long line. Keep in mind that squall lines can occur out to 150 miles ahead of an advancing cold front. So you don't necessarily have to, they're not right immediately along a cold frontal boundary. They could be up to 150 miles ahead of it. So again, like I mentioned, it may fool you a little bit in thinking that a cold front's moved through when it has not. because you'll see with squall lines, you'll see changes in wind speed and direction. You'll see changes in temperature in association with the squall line. You'll see changes in the barometric pressure, and you're thinking that all these signs are indicating a cold front has just moved through your area, but it's not the case again. I've been fooled quite a bit over my time in weather forecasting, where you think that the cold front's through, and then maybe an hour later, after the squall line, the thunderstorms pass through, the winds go back to the southwest, shift back to the southwest. The barometric pressure begins falling again. Temperatures start rising, and you're thinking to yourself, what in the world? I thought that was a cold front. But it turns out it was just the squall line. All right. Here is an example, again, of what I'm showing you is a tilted updraft in association with a supercell. These updrafts are at an angle as they go up with height, and you get what's known as a rear inflow jet, which pushes much colder air from aloft out of the thunderstorm cloud down towards the ground. It's called a rear inflow jet. And whenever you drag a lot of cold air from the top of a thunderstorm cloud down, you're most likely going to drag hail down with it. You're going to drag heavy precipitation with it as well. And you can get these very strong and damaging straight line winds. The National Weather Service will go out and assess damage after severe thunderstorms, or if there's any possibility there was a tornado in the area. They're going to go out and look at that damage pattern. They're going to determine whether it was a tornado or not in their investigation. And a lot of times, it will just simply be strong, damaging straight line winds. These winds can gust up to 70 miles per hour, 80 miles an hour easily, even with some of the stronger supercells in the central plain states. These strong straight line winds can be as high as 100 miles an hour. So just because there's damage, it may just be due to the strong straight line winds, not necessarily a tornado in the area. Okay, now this is a really cool image here. This is a reflectivity weather radar, Doppler weather radar image of a line of thunderstorms. Now notice the bowing out of the line in certain sections, and that's known as the bow echo. Whenever you have a bowing out of a line, a thunderstorm line, that's where you're going to have your strongest wind gusts. Okay, that's where the damage could be the greatest with those straight line winds I just talked about. There's also something known as a derecho, which is a strong straight line damaging wind type storm. There's a lot of momentum. That rear inflow jet is really pushing that cold air down from aloft, so you can actually get these derechos as well. This is actually in southwestern Missouri at this time. And here's an example of a mesoscale convective complex. Notice the circular shape. Now this is an enhanced infrared satellite image. Okay, notice the red circular shape here. The red colors indicate the coldest cloud tops. That means these thunderstorms have grown at great heights, possibly as high as 50 to 60,000 feet in the atmosphere. And it's a large circular area. Mesoscale convective complexes, they continue day or night. Again, they don't necessarily need the heating from the sun to give them that instability. There's so much instability built within this convective system that it kind of just feeds off each other, really. All right. Here's an example of another supercell showing you more of a rotating tube-like structure. This is what would happen with a tornado producing storm, or a supercell that produces a tornado. Some of the main features are shown on this image. It's a really cool image. You notice the overshooting top, the red spiraling circular pattern that indicates a very strong rotating updrafts. And then on the back side, to the left of that strong rotating updraft, you have what's known as a rear flank downdraft, RFD for short. There's very strong vertical wind shear in this case, very rapid change in wind direction and speed with height, which causes that horizontal rotating tube. And once you get these strong updrafts, to take it and pick it up in the vertical, it stretches it out and it forms a tornado. The tornado, one thing I want to mention is the difference between a tornado and a funnel cloud. A tornado is a funnel cloud in contact with the ground. Okay, tornado is in touch with the ground, whereas a funnel cloud is not in touch with the ground, okay? So make sure you know the difference between a tornado and a funnel cloud. Tornado touches the ground, funnel cloud does not. But they're both rotating columns of air. Now, with thunderstorms in general, what you have to look at is the atmosphere in 3 dimensions. So you may have a strong low pressure system at the ground, at the surface, very strong cold front. You got a very strong storm system. You get supercell thunderstorms that form out ahead of the cold front at the surface. And that is really, it's all connected to the 5,000 foot level, the 10,000 foot level, the 18,000 foot level, and even the 30,000 foot level at the jet stream, the polar jet stream. All of those levels play into creating wind shear, an extra energy, extra dynamic energy in the atmosphere. Whenever you get these strong changing wind speeds and directions with height, you're going to get turning of the winds. And you get that turning of the winds, and you can get rotation, what's known as a mid-level rotation or mesocyclone, associated with a supercell thunderstorm. In this case, I'm showing you southerly winds, south winds at 5,000 feet, southwesterly winds at 10,000 feet, and then you got colder air aloft. When you get colder air over warmer air, you have great instability in the atmosphere. That's going to allow the air to want to rise more vigorously. You've got a lot of rotation, a lot of wind shear here in this case with a supercell. And then you have what's known as a jet streak or jet maximum up at 30,000 feet. And what that does is it removes mass aloft really quickly. And when that mass is removed aloft really fast, more air comes in from below and rises more rapidly to replace the air in that mass aloft. Okay, so when you're talking about severe thunderstorms, you're looking at multiple levels, from the ground all the way up to the polar jet stream level at 30,000 feet. You really are. This is an example. This chart here shows you the average number of thunderstorm days. These are thunderstorm days in the United States. You notice where the capital is. The capital of thunderstorms in general is Florida. The Florida Peninsula has the most number of thunderstorms each year. Look at the number of thunderstorm days, 90. What is a thunderstorm day? It's just simply a day in which you hear thunder. Okay? So you're looking at 75 to 90 thunderstorm days on average a year in Florida. The Gulf Coast in the purple shading, not that far behind. 65 to 70 thunderstorm days. And then as you move further north in the United States, you notice how the numbers drop, which is what we would expect. As you get further into the North American continent and the United States in general, your number of thunderstorm days will drop because you're getting cooler temperatures the further north you go, and then also you're having less moisture available. Okay, thunderstorms really rely on moisture. The main 3 key ingredients in thunderstorm development, really, it comes down to a lot of moisture, lift, and a lot of warmth. So you want warm temperatures, lift, and moisture, and you typically will get some type of thunderstorm. Right. Notice out in the western U.S. here now. Now this is interesting, okay? This is the average number of hail days each year. Notice there's a purple shading area in southeast Wyoming into northeast Colorado. They average 8 days with hail each year, okay? But now look at Florida. There's nothing there. We just looked at the previous slide and we saw that Florida has the most number of thunderstorm days, the most number of thunderstorms each year, but yet they don't have any number of hail days. So what's going on with that? Why is there more hail over southeast Wyoming into northeast Colorado? And it has to do with the fact that thunderstorms, generally, the freezing level is much lower, first of all. Higher elevation thunderstorms, generally, the base of the cloud, the distance from the base of the cloud, the thunderstorm cloud, and the ground is much less. Not to mention that you're higher in elevation, so your freezing level is much closer to the ground there. All right. The average freezing level in Florida, the peninsula there, Florida Peninsula, may be 13 to 14,000 feet. So yes, you may have hail that forms within a thunderstorm cloud in Florida, but the freezing levels are much higher. What does that mean? That means that that hail is going to melt and just form as big raindrops when it hits the ground in Florida. Over southeast Wyoming and northeast Colorado at higher elevation, you're going to have the freezing level much closer to the ground, so the hail does not have time to melt before it hits the ground. So you get larger hail. The higher frequency of hail occurs out in Colorado and Wyoming, believe it or not. So just an interesting fact there. All right, so this image here, what I'm showing you is that rule. When you see the lightning and then you hear the thunder, on average, 1 mile is equal to 5 seconds. So if you see a flash of lightning, it takes 5 seconds before you hear the thunder, then you knew that the lightning was basically 1 mile away. Let's say you see a flash of lightning and you hear the thunder about 10 seconds later. Between lightning and thunder is about a 10-second window. Then you know that your lightning was about 2 miles away. So just remember that. For every mile, it's 5 seconds difference between seeing lightning and hearing thunder. Okay, and just realize that the speed of light is much faster than the speed of sound, and that's why you see lightning first, and then you hear the thunder later. Here's an example of the different charges, electrical charges associated within the thunderstorm cloud itself. You got these strong updrafts, and you get these hailstones, hailstones actually become more negatively charged, and then you get colder ice crystals at the top of the cloud that are positively charged. So you can imagine that electrical difference between these hailstones, which are negatively charged, and the ice crystals at the top of the cloud, which are positively charged, creates this electrical difference or electrical potential. And once that electrical potential or difference gets too great, then you see the flash of light we know as lightning. Right? And here is the charge distribution, the electrical charge distribution within a typical thunderstorm. As I mentioned, you typically get positive charges with ice crystals in the upper part of the cloud, mainly negative charges at the base of the cloud with the liquid drops, and then basically they call it a shadow effect. Directly beneath a thunderstorm cloud, you get a positive charge. So when the positive charge, lightning actually works its way from the ground up, surprisingly, from the ground up to the base of the cloud. Positive charge generally towards a negative charge in the lower part of the thunderstorm cloud. That creates that stepped leader. Okay. Here is exactly that. So you get a step leader. The charge is initiated from the positive, for example, trees. That's why they tell you never want to be near or located taller objects at the ground during a lightning storm, because the positive charges are basically streaming up those taller objects, and they're trying to meet up with the negative charges coming down out of the thunderstorm cloud. Where they meet, you typically get a step leader and eventually a return stroke. Okay, and here's the different types of lightning. I kind of alluded to the fork lightning, how it has multiple branches. Ribbon lightning is mainly one stroke of lightning in the middle there, the upper portion there in the middle. Bead lightning kind of looks just like that, like beads. You don't really see that too much, and you really don't see the ball lightning either as much. It's kind of a rare type of lightning. And then sheet lightning is just what you typically would see, the normal flash of lightning in the sky. And then heat lightning, believe it or not, there is something known as heat lightning. Okay, heat lightning, typically the thunderstorm is too far away for thunder to be heard. When it's heat lightning, growing up in the Midwest, I can remember many late summer nights where you would see lightning flashing, typically sheet lightning, but you don't hear any thunder at all. We didn't hear any thunder, and it was so intriguing because you're thinking, well, there should be thunder with that. But it's because of the distance of the thunderstorm. It's so far on the horizon, so far away from your location, you never really hear the thunder. So heat lightning is, typically occurring on a hot, humid night in the summer. You'll see flashes of light, you just don't hear the thunder. That thunderstorm is just so far off. Okay, and then this is showing you an example of how taller objects such as flagpoles can really be an attraction or a magnet for lightning strikes. It is a myth. It is a myth that lightning never strikes the same place twice. It does strike the same place twice, and it has. If you look at taller buildings within our major cities in the United States, such as the Empire State Building, That Empire State Building has been struck multiple times, multiple times. Even during one thunderstorm, it can be struck multiple times by cloud-to-ground lightning. So that is a myth. When you hear that lightning never strikes the same place twice, that is a myth. You got positively charged ions or electrons that are positively charged ions that are moving up taller objects and attracting the lightning. All right, now we move on to our final topic of the lesson today, and we're going to talk about tornadoes. Very interesting topic. Tornado occurrence and distribution. Who gets the most tornadoes in the United States? Well, we know this area as Tornado Alley. These are the states that get the most tornadoes on average in the U.S. States such as Kansas, Oklahoma, North Texas, Nebraska. That is true Tornado Alley. Okay, and it's a tornado alley because you get continental polar air that come in with cold fronts from the northwest, from Canada, and then you got this warm, moist, maritime tropical air mass coming in off the Gulf of Mexico. And when those two meet, it's such a contrast in air masses that it creates rapidly rising air along a frontal boundary, a cold front typically. And once that happens, the air rises vigorously, violently, and you get these very tall supercell thunderstorms that form. They can be as high as 70,000 feet in height in the Central Plain states and Tornado Alley. And you get enough wind shear, turning of the winds, jet stream, upper level jet stream blowing overhead. You're going to get a lot of turning and twisting of the wind, and that's why they get so many tornadoes there. Plus, the geography of the area is flat. When you look at Oklahoma, Nebraska, Kansas, it's very flat. So there's really nothing getting in the way of modifying the air masses. Nothing is set up to really deflect air masses. They're meeting head-on with full force in that part of the United States because of the flat land. There's another secondary higher area of tornado occurrence, and that's known as Dixie Alley. This is basically in the deep south, Mississippi, Alabama, in that area there. There's actually 2 tornado seasons in Mississippi, 2 of them. There's one in the spring time period, and there's another one in October into November. Like right now would be the second peak of tornadoes down in the deep south in Mississippi, for example. I did live in Mississippi for a little bit, and there have been some tornadoes or close calls that we had when I lived there in November. So it does match up fairly well. Moving on to tornado winds now. The tornado winds are measured by Doppler radar. Doppler radar uses a velocity product and has different color schemes or codes indicating when air is moving away from the Doppler radar site and when air is moving towards the Doppler radar site. You can get multi-vortex tornadoes as well. These are violent tornadoes that contain smaller whirls that rotate within them. There's something known as multiple vortex, or it's also known as multiple suction vortices. And you get one main tornado, and then you get these small little whirling eddies, additional little tornadoes that kind of spin around the main tornado. Seeking shelter, typically the best spot to go for tornadoes is in the basement. If you don't have a basement, a storm shelter, or even a safe room. Some of these houses today are being built with, they're being tested to withstand hurricane force and tornado force winds, and they actually build these special rooms that can withstand such force. They've been tested, and they're called safe rooms. All right, so what are the different tornado watch? What's the difference between a tornado watch and a tornado warning, a tornado emergency? A tornado watch is when tornadoes are likely to form during the next few hours. Okay, so tornado watch just means conditions are favorable for tornado formation. Tornado warning is when a tornado has actually been spotted either visually by someone or via radar, that Doppler weather radar, the reflectivity image. And typically on a Doppler weather radar, a tornado is going to have more of a hook echo or a hook shape. Tornado emergencies, those occur generally when you have a strong tornado threatening a populated area. And an example is Oklahoma City, Oklahoma. Take a look, Google this, Google Oklahoma City tornadoes, and you will see some amazing video footage that people have made of some very long-lasting tornadoes that have moved through Oklahoma City or the general surrounding more populated suburb areas of Oklahoma City, and it is incredible to watch the video. These tornadoes can become so wide, and they are so damaging. We use the enhanced Fujita scale, the EF scale, and it's based on tornado wind speed, the classification of the enhanced Fujita scale. And you can have EF4s and EF5s, EF5 being the strongest on the enhanced Fujita scale, just going right through a very populated area. And in this case, they would issue a tornado emergency. Right. So the enhanced Fujita scale. Okay. So Dr. Theodore Fujita, they called him Mr. Tornado, by the way. He did a lot of extensive research, especially in the 1970s, on the patterns, the damage patterns created by tornadoes. So what Dr. Fujita would do is, after major tornadoes struck areas, for example, the 1974 super outbreak, the Palm Sunday outbreak, he would, after those kind of outbreaks, he would literally get into a plane and look at the damage patterns, the damage pattern from above an airplane. And he noted he did a lot of research and noted a lot of interesting things with those damage patterns, the whirling suction patterns of a tornado after it happened. Fujita initially came up with a scale named after him, the Fujita scale, and it classifies tornadoes according to rotational wind speed. Okay. Now, it was determined later that we need to also throw in a wide range of criteria in estimating a tornado's winds. And so we developed, there's a new scale, it's called the Enhanced Fujita scale. It's actually not new anymore. It's actually been in use for quite some time. But it uses a set of 28 damage indicators now. Okay, so we've kind of broadened the Fujita scale, and now we're looking at other criteria in determining, okay, what was that? Was that an EF1 tornado, an EF3 tornado? The National Weather Service, as I mentioned, they go out and they go out and look at the damage patterns. They do assessments after possible tornadoes strike an area. There's a team from the National Weather Service that goes out with these kits, and they go out and look for the damaging patterns in determining not only if it was a tornado or straight line winds that would cause the damage. They will also classify that tornado based on the set indicators. Right. So the deadliest tornadoes actually occur in what are known as tornado families. Okay. They're a group or series of tornadoes spawned by the same thunderstorm. Deadliest tornadoes. So when we talk about tornado families, we're talking about an extreme case in which the atmosphere is very prime that day for some very significant thunderstorms to develop. And those could be long-lasting tornadoes, usually are associated with these tornado families. Tornado outbreaks are classified as large number of tornadoes, by the way, and they typically are 6 or more tornadoes that form over a particular region. So tornado outbreaks, we've had some famous ones. Take a look at here's some interesting tornadoes if you want to take a look at them, if you have a few minutes. Google the Tri-State Tornado of 1925. It traveled across 3 states, and it was one of the more significant tornadoes in U.S. history. The Palm Sunday outbreak of 1974, another very large tornado outbreak. Check out the ones, I think that was 2010, 2011, somewhere in there in Alabama. There was another large tornado outbreak with some very strong EF4, EF5 tornadoes that did a lot of tremendous damage. So check out some of those major outbreaks in the recorded history of the United States. And then I challenge you to look at the Tornado Project. If you Google the Tornado Project, you can actually order tornado posters. You can actually order tornado videos as well. It's a really cool place. It has a lot of cool tornado facts in it, the Tornado Project. It's really cool website. All right, so this is the average annual tornadoes per 10,000 square miles chart. Oh, wow, look at out west. Look in the western United States. The source on this image is NOAA. And by the way, look at out west there. There's hardly any tornadoes. Wow, I wonder why. Well, the West Coast in particular has the cold California current offshore. And the West Coast also sits on the stable side of a East Pacific anticyclone, or a stronger subtropical high, and on the front side or east side of that is very stable air. So you got a cold current and stable air. You just don't get a lot of tornadoes out west. If you look at the Central Plain states, though, right there in Kansas, 11.7 average annual tornadoes per 10,000 square miles. So, if you move to Kansas at any point, or if you live in Kansas, I'm sure they probably recommend that you get some type of insurance for your house. Also, look at the Midwestern United States, Illinois 9.7, Oklahoma 9.0, and Dixie Alley. Look at Mississippi and Alabama. There's some orange shading there. 9.2 in central to southern Mississippi, and 8.6 in the northern Alabama. That's that secondary area of, tornado alleys out over Nebraska, Kansas, Oklahoma. And then you have that secondary Dixie Alley, which is Mississippi and Alabama. And see that? Look at that. So it kind of matches up with what we talked about as far as the frequency goes. This is a chart showing you the number of tornadoes throughout the year. Okay, so on the y-axis, that vertical axis on the left, I have number of tornadoes ranging from 0 to 350, and on the bottom, the x-axis, I'm showing you the months of the year, January through December. And look at, what do you know? Springtime has the greatest frequency of tornadoes. The spring season has the greatest frequency of tornadoes, especially April. May is the greatest number of tornadoes on average in the U.S., just below, basically between 275 and 300 tornadoes in the month of May. The second highest month is June at 225 tornadoes, okay? And you notice how the numbers, or how these bar graphs, how they drop off in the winter months. We just don't have the clash of the air masses as much anymore. We have much colder air that's pouring south out of Canada at this time, so the instability is not as great during the winter months. So your tornado numbers are much lower. But you can still get tornadoes any time of the year. As you notice, there is a number of tornadoes that does occur in January and December, the coldest months for the United States. So can't necessarily let your guard down. Even in wintertime, tornadoes are possible. Okay. Here's an example of a tornado and its movement. Tornadoes typically move from the southwest to the northeast across the United States, and they typically do so as they kind of like follow the jet stream winds. Not only that, they follow the winds out ahead of an advancing cold front. Tornadoes typically occur out ahead of an advancing cold front, so they typically move from southwest to northeast in the United States. Here's an example of a suction vortice. These are showing you multiple suction vortices. So you have a main tornado that is spinning, dropping down from a wall cloud. Tornadoes do drop down from wall clouds. So you have a main tornado, and then you have these spinning little mini tornadoes that are kind of rotating around the main suction vortex, or the main tornado. So these are called suction vortices. And you could have multiple ones. There's some cool videos out there. You can actually see tornadoes, like mini suction vortices, spinning around a main tornado. This has happened before, and it does occur. All right, so we're getting close to the end of the lesson, and we're going to talk a little bit about tornado formation as we wrap things up. The basic requirements for tornado formation are a conditionally unstable atmosphere. Supercell thunderstorm is, you want a supercell thunderstorm for tornadoes, and then you want strong vertical wind shear. All right, supercell tornadoes, they're going to form with the supercell thunderstorms. Now, we talked about some of the unique characteristics of supercells compared to the ordinary cell or air mass thunderstorm. One of the big criteria for supercells is very strong vertical wind shear. So there's a very abrupt change in wind speed and direction with height with supercells. Another thing we mentioned about supercells that makes them special is the tilted updraft. They have a tilted updraft, which allows the updraft to continue higher and higher into the atmosphere without being choked off. So the downdraft is kind of off to the side. The tilted updraft is its own area of the thunderstorm. So the air continues to rise vigorously with a supercell. Right. So with supercell thunderstorms, you get tornadoes. All right. And the hook echo is an example of what you would look for on a radar image, a Doppler weather radar image, a reflectivity image. You would see a hook type shape. And that's an indicator by the National Weather Service. If they see that hook echo, that hook shaped and reflectivity, they are going to most likely issue a tornado warning. Tornado genesis is just simply the development of a tornado. Okay, whenever you see a hook echo, that's what they're thinking. Okay, well, we're about to get a tornado. We better issue a tornado warning now. Okay. Non-supercell tornadoes, those also can occur. So, yes, supercell thunderstorms typically produce the most number of tornadoes, but you can also get what's known as non-supercell tornadoes. These are tornadoes that do not occur in association with the pre-existing wall cloud of a supercell. Examples of non-supercell tornadoes include gustnadoes, which typically form along the leading edge of strong downburst of winds pouring out of a thunderstorm, land spouts, and then cold air funnels. What's interesting about cold air funnels, I've seen these before, and you get extremely cold air aloft over relatively warmer water. And cold air funnels typically form over water. I've seen them in Virginia. I've seen them also even out in California. There's cold air funnels when you get a really cold pocket of air aloft and you get any kind of heating, just temporarily heating at the ground. It creates a very strong temperature gradient in the vertical, a very large difference in temperature between the ground, and let's say, as an example, 18,000 feet, and you get what's known as cold air funnels. And again, they typically form over relatively warmer water. Very cold air aloft over relatively warmer water will produce cold air funnels. Here's an example of an image of a tornado formation. What you kind of have going on in the thunderstorm, and in this case we're showing you a supercell. You have a inflow notch at the bottom right hand corner of the image. It's called an inflow notch, and the circulation kind of wraps in and around cyclonically. You'll notice the shape at the bottom of the reflectivity image here is a hook, and that's exactly what I was talking about with a hook echo. This is the way it would appear on a Doppler weather radar. How do tornadoes form again? I was kind of explaining this, but now I'm kind of glad I got this graphic to show you. It'll help further emphasize it. Generally, you get wind directions over a short distance in the vertical. The wind directions are changing rapidly. Whenever you get changing wind directions over a short vertical distance, you get a rolling, spinning type vortex, a rotating tube of air that kind of it forms in between these layers. And when that happens, you get a strong enough updraft there on the right-hand side. The right-hand image shows you a very strong rotating updraft. It's taking that rotating, the horizontally rotating tube, and it's lifting it up in the vertical, right? And when that happens, you get a tornado to form. So really it comes down to wind shear when it comes to tornado formation. It really does. A large directional change in wind direction over short distances in the vertical. Here's an example of a tornado from a side view, showing you the warm inflow. Then on the back side, you get that rear flank downdraft, which has a much cooler air. So you get this very rapid spinning motion associated with the warm inflow and then that rear flank downdraft. And you get what's known as a mesocyclone to form, which is a rotating column of air in the mid-levels of the atmosphere. There's actually mesocyclone alerts on a lot of these Doppler weather products that meteorologists can use to determine if you have a mesocyclone. Then they know if there's a rotating mid-level updraft. They got to be very, very closely monitoring that storm for possible tornado development. Okay. Moving on now to more on tornado formation. Just showing you that you get updrafts, you get a rapidly changing wind direction over a short distance. You're going to get a lot of spin in the atmosphere. You get that spin, there's a good chance you can actually get a tornado develop. And in this example on the right hand side, I'm showing you a land spout. Water spouts are kind of unique in that they're a rotating column of air connected to a cumuliform cloud over a large body of water. So water spouts are basically tornadoes over water, if you want to think of them like that. I did see a few water spouts out over the water last December, and it's a really cool sight to see. You get this really cold air aloft over the relatively warmer water, and you create a possible water spout. Tornadic water spouts are tornadoes that formed over land and then traveled over water. So a tornadic water spout is one that starts on land as a tornado, and it kind of just moves out over the water. Fair weather waterspouts, they're not associated with supercells that form over water, especially above warm tropical coastal waters. Sometimes you can see these harmless looking waterspouts. You can be on the beach and you can look out over the water in the Gulf of Mexico or over Key West. If you ever go down to Key West, you'll see a lot of these waterspouts that form, and they're known as fair weather waterspouts. Why? Because there's really no supercell thunderstorms in the area. They just happen to be forming over relatively warmer waters where there's a lot of instability and moisture. And that's really it. I wouldn't want to take a boat out into one of these though, because they could still cause some damage. Right. So observing tornadoes and severe weather, if we look at Doppler radar, weather radar principle, I was telling you earlier that there's different color schemes associated when you look at a Doppler weather radar velocity product. It shows you when air is coming towards the radar and when air is moving further away from the radar. And whenever you have air moving close, you have a color that shows that the airflow is moving towards the Doppler radar, and it's right next to a portion that shows airflow moving away from the Doppler radar. There could be a vortex there, some sort of spinning motion. It's called gate-to-gate shear. Large speed changes over a short distance or large directional changes on the Doppler weather radar over short distances could possibly yield a hook echo and a tornado. Okay, so let me show you some images here. So this is a velocity product, and this is right outside of Tuscaloosa, Alabama. I don't know the year of this one, this image, but it may have been one of those super outbreaks I was alluding to earlier, 2011 I think it was, when Alabama really got hit hard with a bunch of tornadoes, and they were very intense tornadoes. This is an example of a tornado vortex signature on a velocity product. Just keep in mind that whenever you have a brighter red color next to a green color, that generally indicates rapid speed or velocity changes of the air. So whenever those two are touching each other, we call that gate-to-gate shear. Now you don't need to worry about knowing that for the course, but it's an indicator to meteorologists that you could have a rotating mesocyclone at that point, and that eventually could yield a tornado. You may soon see a hook echo on the reflectivity of the weather radar. But this velocity product is very useful because the cooler colors generally are moving towards the Doppler radar. The greens and the blues would be going towards the radar, and the reds, the brighter colors, go away from the radar. So you have, in this case, where the tornado vortex signature is, you have red colors touching green colors, so you have a rapid change of motion of the wind between the red and the green here in this case. Storm chasing, you could sign up for storm chasing tours now. They offer them on the Central Plains. I've never been able to get out there. I would really love to sometime just to kind of experience it. But storm chasing, generally in the form of tour groups, they offer it. You can go out there on a little tornado safari if you like. Also, there's risk activity even for veteran researchers. It's a risky activity. We've had some storm chasers killed. You really got to know the ins and outs of tornadoes before you get out there. I know we were popularizing everything for a while there in the late 90s with the movie Twister, and then all of a sudden everybody became storm chasers, and you really got to know what you're doing though to stay safe. Vortex is Vortex and Vortex 2 were field studies that were done on tornadoes. If you watch some of the Weather Channel, Mike Bettis, he'll talk about it. He was on one of these Vortex experiments. So he went out to the Central Plains and they chased tornadoes, and there's a lot of scientific research that's going on in these Vortex and Vortex 2. Vortex standing for Verification of the Origin of Rotational Tornadoes experiment. So the research in the field continues to this day. We're trying to know more and more about tornadoes because obviously they could be very life-threatening events. So we're trying to really get to know more and more every day about tornadoes as much as possible. So research does continue in this area. Okay, so to wrap things up today on this lesson, we talked about thunderstorms and tornadoes. You can find both of these topics in Chapter 10 of your textbooks, 7th and 8th edition. Thunderstorms are convective storms that produce lightning and thunder. And then there's a special type of thunderstorm that typically produces tornadoes known as a supercell thunderstorm. These are intense thunderstorms with a single rotating updraft, and it's a tilted updraft at that. Additionally, we talked about your ordinary cell air mass thunderstorms. Those typically form during the hottest time of the day, the heating of the day during summer, when you have the greatest amount of heat and instability, and they generally dissipate after sunset. We also talked about multi-cell thunderstorms. Examples include mesoscale convective complex, as well as we talked about squall lines, which typically form up to 150 miles ahead of an advancing cold front. Additionally, we talked about tornadoes and that they're rapidly rotating columns of air with a circulation that reaches the ground. They form within supercell thunderstorms, and they also can form in non-supercell thunderstorms as well, as we talked about with land spouts, water spouts, and so forth. Okay, that wraps it up today on the lesson on thunderstorms and tornadoes. I hope you had an enjoyable time learning about this topic. Please feel free to ask me questions at any point. You know how to reach me. And that wraps it up today. I hope everybody enjoyed it, and I wish everybody a great and pleasant day.